Welcome to the deep dive. Have you ever looked at the world of machine learning algorithms and just thought, that feels like a total black box?
Yeah, like there's this incredible power, but how it actually works seems locked away.
Exactly. Secret language stuff. If that sounds familiar, well, you're definitely not alone.
hmm
And that's really why we're here today. Our mission for this deep dive, cut through that complexity.
Right. Give you that gut feeling, that intuition.
Yeah, help you understand which algorithm might actually be the right choice for a specific problem you might face. Less overwhelm, more clarity.
It's all about demystifying it, isn't it? Taking something that seems really complex and just showing the core ideas.
The fundamentals, without getting totally bogged down in the complex math behind it all.
Exactly. We want you to get the intuition.
Okay, so let's unpack this. For anyone who maybe needs a quick refresher, what is machine learning at its heart?
Well, at the broadest level, machine learning is a field within AI, right? It's focused on developing these statistical algorithms that learn straight from data.
Okay, learning from data.
Yeah, and crucially, they then generalize that learning to new data they haven't seen before. And they do this without needing explicit step-by-step instructions for every single situation.
So they figure things out themselves based on examples.
Pretty much. And what's really fascinating, I think, is how much of the amazing AI progress we see everywhere now.
The stuff in the headlines daily.
Right. So much of that is driven by one specific type of algorithm, neural networks. We'll definitely talk more about those later.
Okay, good. So it's systems building their own understanding rather than us coding every single possibility. That makes sense. Now, looking at the big picture, you often hear about two main areas within machine learning: supervised and unsupervised learning. Let's maybe start with supervised.
Okay, supervised learning. This is where you have a data set that includes both your input variables, we usually call these features.
And things you measure, like size or color.
Exactly. And you also have a known output variable, the target or label that you want the machine to predict.
Ah, so you already know the right answer for your training data.
Precisely. Think of it like a teacher supervising a student. You give the algorithm training data, where every example comes with the true value or the label.
Got it.
The algorithm then learns the mapping, the relationship between those features and the labels.
So it can then predict the output for new data where the label isn't known.
That's the goal.
So that's like showing a toddler pictures
Right.
and saying, this is a cat, this is a dog, cat again. You've provided the labels.
Perfect analogy.
Then you show in a picture and ask, what's this? And the magic is, hopefully, it recognizes a cat it's never actually seen before.
Exactly. And concrete examples. Predicting house prices. You have historical data, square footage, location, age.
And the actual price they sold for, the label.
Right. Or classifying an image as a cat or dog based on its pixels because
Yeah.
you've trained it on thousands of images that were already labeled cat or dog.
Okay, that clicks. But then, what if you don't have those labels? What if you just have a pile of data? That's where unsupervised learning fits in.
Precisely. Unsupervised learning is for problems where you simply don't know the truth or the labels beforehand.
Okay.
So, sticking with your analogy, supervised learning is giving the kid labeled pictures. Unsupervised is like handing that same kid a big pile of animal pictures.
But they've never been told what a cat or dog is.
Exactly. No prior knowledge. And you just say, okay, group these based on how similar they look. No other instructions. The algorithm has to find the patterns itself.
So it has to figure out, okay, these furry things with pointy ears seem to go together, and these bigger ones with trunks go over here. It finds the groups on its own.
Yes, it discovers the underlying structures.
Like my email sorting itself into promotions or social without me ever defining those categories initially.
That's a perfect real-world example. It finds the patterns, creates the groups, the clusters, and maybe we label them later, but the algorithm found them first.
Okay, cool. Let's dive a bit deeper into supervised learning then, because you hear about that one a lot. It seems more common, maybe.
Arguably, yeah. A lot of common prediction tasks fall under supervised learning.
And once we're in supervised territory, there's another split, right? Regression versus classification. Can you walk us through that?
Absolutely. So, regression. Here, the goal is to predict a continuous numeric target variable.
A number that can be anything within a range.
Right. Think back to the house prices. We're trying to predict a specific dollar amount. Could be $300,000, could be $300,500, could be anything in between.
And the algorithm might find patterns like, more square footage generally means a higher price.
Exactly. It finds those relationships. Maybe square footage has a strong linear link to price, but maybe the age of the house has a more complex effect. or almost none at all.
Okay, so regression predicts a value on a scale, and classification is different how?
Yeah, classification is a different beast. Here, we're trying to assign a discrete categorical label, a class.
So not a number, but a category name.
Exactly. The classic example is email,
Mm-hmm.
spam or not spam. The output isn't a continuous value. It's one of a limited set of distinct categories.
And it's not always just two categories, is it? Like my Gmail has more than just junk or inbox.
Right. You could have multiple classes. Gmail has junk, primary, social, promotions, updates, loads of them.
And each email gets put into just one of those buckets.
One specific predefined bucket, yes.
All right, makes sense. So let's open up the toolkit. Let's look at some specific supervised algorithms. And I guess we have to start with the big one, the classic. Linear regression, sometimes called the mother of all algorithms.
That's a good place to start. At its core, linear regression tries to figure out a linear relationship between your input features and your output variable.
Finding a straight line trend.
Essentially, yes. The algorithm fits a linear equation to your data. And how does it do that? It finds the line that minimizes the sum of the squares of the distances. Basically, it minimizes the average prediction errors.
Okay, trying to get the line as close as possible to all the data points, on average.
That's the idea.
Like, if you plot height against shoe size, a linear regression might tell you, okay, for every one size bigger in shoes, the person tends to be, say, 2 inches taller.
That's a perfect intuitive example. It defines that average linear trend.
Simple concept, but powerful.
And here's where it gets really interesting. While that sounds basic, you can extend this.
How so?
Well, you can use it with multidimensional data. For your shoe size example, you could add gender, age, ethnicity, lots more features. The model becomes more complex, finding relationships across all those inputs.
Ah, okay. So it's not just one input predicting one output.
Right. And honestly, a lot of the really fancy algorithms we hear about, even neural networks, are in a way extensions of this fundamental idea, finding patterns and relationships in data, just in much more complex ways.
So even those huge neural nets have roots tracing back to just fitting a line? That kind of puts things in perspective.
It does. They build on these core principles.
Okay. Now, linear regression is great for numbers, for predicting how much. But what if the question is which one? Which category? That's where logistic regression comes in, right? Kind of a cousin.
Exactly. Logistic regression is a variant, but it's built for classification, not predicting a continuous number.
So how does it adapt?
Instead of fitting a straight line, it fits something called a sigmoid function. It looks like an S-shaped curve.
Okay.
And what that curve does is take any input value and squash it, basically, into a probability between 0 and 1.
Ah, so the output isn't the category itself, but the chance of it being in a category?
Precisely. It gives you the probability that a data point belongs to a certain class. Like, it might say there's an 80% probability that someone who is 180 centimeters tall is male, based on the training data.
Got it. Still finding a relationship, but outputting a probability for a category. Clever tweak. Okay, next up. K-nearest neighbors, or KNN. This one always feels almost too simple.
It is remarkably simple and intuitive, and that's often its strength. It's frequently a great first model to try.
Why is that?
Because it's non-parametric. That means it makes very few assumptions about how the data is structured. It can handle really complex, wiggly relationships without needing a specific mathematical formula up front.
Okay, so how does it work then, if there's no equation?
The core idea is just this. For a new data point you want to predict, you look at its K closest neighbors in the training data.
K neighbors, K being a number you choose.
Right, and you predict the target for the new point based on those neighbors. If it's classification, you take the majority vote of the neighbors' classes. If it's regression, you take the average of their values.
So if I want to guess someone's gender based on height and weight, I find the, say, 5 people closest to them on a height-weight chart.
Mm-hmm.
And if 4 out of 5 are female, I predict female. It's all about who you're near.
Exactly. Or for regression, predicting weight. Find the 3 people closest in height and chest size and predict the new person's weight as the average of those 3. It relies on that intuitive idea that similar things are close together.
Makes sense. But that K, how do you pick K? Seems pretty critical.
You're absolutely right. K is what we call a hyperparameter. Choosing the right K is definitely part art, part science.
What happens if you get it wrong?
Well, if K is too small, like K1, your model might be perfect on the data it trained on, but terrible on new data. It's basically just memorize the training set. That's overfitting.
Okay, too specific.
Yeah. But if K is too large, you might smooth things out too much and miss the real patterns. You get a poor fit everywhere. That's underfitting.
So you need the just right K, like Goldilocks. Have you seen projects where a bad K choice really caused problems?
Oh, absolutely. A tiny K can make the model incredibly sensitive to just one or two noisy or weird data points,
Yeah.
leading to bizarre predictions.
Right.
And a huge K can just wash out all the interesting local detail, making every prediction look like the overall average. It really shows how much tuning matters.
Fascinating balance. Okay, moving on. Support vector machines. SVMs. I always picture these as like expert boundary drawers.
That's a great way to think about them. The main idea behind SVMs is to find the decision boundary that best separates data points from different classes.
Okay.
Imagine you're classifying cats and elephants based on weight and nose length. An SVM tries to draw a line between the cat data points and the elephant data points.
But not just any line, right? There's something special about the SVM line.
Exactly. It finds the line that has the largest possible margin, the biggest empty space between itself and the nearest points of each class.
Maximizing the buffer zone. Why is that important?
That large margin makes the model generalize better to new data and makes it less sensitive to noise or outliers near the boundary. It's more robust.
Okay. And what are the support vectors then? Are they the points on that margin?
Precisely. They're the data points right on the edge, defining the margin. The cool thing is, the SVM only needs those points to define the entire boundary. That makes it memory efficient.
So it focuses on the critical data points.
Yes. And what's really fascinating is how powerful SVMs are. They work well even in really high dimensions, say hundreds or thousands of features. The boundary becomes a hyperplane then.
A higher dimensional flat surface.
Sort of, yeah. And they have this amazing trick called kernel functions, the kernel trick.
Okay, what does that do?
It lets them find really complex nonlinear decision boundaries. Wavy lines, circles, complex shapes.
Ow.
It's like they implicitly create new, more complex features from your original ones, like automatically calculating BMI from height and weight without you telling it to, and find the boundary in that higher dimensional feature space. It's mathematically elegant.
Wow. So they can find really complex patterns efficiently, even nonlinear ones, without needing explicit instructions on what features to create. Powerful stuff.
Very powerful.
All right. Next, naive Bayes classifier. The naive part always makes me curious. Why naive?
It's called naive because it makes an assumption that's usually false, but simplifies things massively. It assumes that the probability of different features appearing are independent of each other.
Meaning?
Well, take spam filtering. It assumes the chance of the word Viagra being in a spam email has no relation to the chance of the word money being in that same email.
Which probably isn't true in reality, right? Those words might often appear together in spam.
Exactly. That's the naive part. But here's the thing. Even with that false assumption, naive Bayes, which is based on Bayes' theorem from probability,
Okay.
it works surprisingly well. And it's incredibly fast and computationally efficient, especially for text classification like spam filters.
So how does it actually filter spam then?
You train it on lots of emails you've already labeled as spam or not spam. It counts how often each word appears in the spam emails versus the non-spam ones.
Building probability tables for words.
Right. Then, when a new email arrives, it looks at the words in it and multiplies their individual probabilities of being spam or not spam together to get an overall score.
And classifies it based on that score.
Yep. Super fast, often good enough, even if the independence assumption is technically wrong. It's a workhorse.
A smart shortcut for speed. Okay, moving on to decision trees. These feel very, flowchart-like. Intuitive.
They really are. A decision tree is basically just a sequence of yes-no questions about the features that splits the data down.
Like playing 20 questions with your data.
Kind of. Imagine trying to classify heart attack patients as high or low risk. The first question might be, is their blood pressure over X? If yes, maybe the next is cholesterol over Y? Each question splits the group.
And you keep splitting.
Until you get to the end nodes, the leaves of the tree. And the goal is to make those leaf nodes as pure as possible.
Meaning they contain mostly, or ideally only, data points of one single class, minimizing mistakes in the final groups.
Exactly. You try to find the questions, the splits that best separate the classes at each step.
So a single tree seems straightforward, maybe a bit basic.
A single tree can be basic and often prone to overfitting learning the training data too specifically. But here's the key insight.
There's more to it.
So what does this all mean? The real power isn't usually in one tree, but in combining many simple decision trees together. That leads us to ensemble algorithms.
Ensemble, like a musical ensemble. Strength in numbers.
Precisely. combining multiple models to get a better result than any single one could achieve alone.
Okay, tell me about the main types. First, bagging and random forests.
Okay, so bagging, which stands for bootstrap aggregating, is about training multiple models, like decision trees, independently. Each model gets trained on a different random subset of the original training data.
So each model sees slightly different data.
Yes, and a very famous, very effective type of bagging using decision trees is called a random forest.
Forest. Because it's many trees.
Exactly. It builds a whole forest of decision trees. For classification, each tree votes on the final class. For regression, their predictions are averaged.
Okay, and what's the random part? Just the data subsetting?
That's part of it. But there's another crucial bit of randomness. When each tree is deciding on a split the yes-no question, it doesn't get to look at all the features. It only considers a random subset of the features available at that split.
Why do that? Why restrict its view?
That's key to preventing overfitting. It stops any single tree from becoming too reliant on one or two very predictive features. It forces the trees to be diverse.
Ah, so the randomness makes the whole forest more robust, less likely to fixate on noise in the training data.
Exactly. Different perspectives, combined wisdom. Very powerful.
Okay, so that's random forests, parallel trees, voting. How does boosting differ? It's another ensemble method, right?
It is, but the philosophy is quite different. Bagging trains trees in parallel, independently. Boosting trains them sequentially.
One after the other.
Yes. Each new tree, or model, in this sequence specifically tries to fix the mistakes that the previous models made.
So it focuses on the hard-to-classify examples from the last round.
Pretty much. You start with a simple model, find where it messes up, build the next model to pay more attention to those errors. Repeat. You're building a series of weak learners that together form a very strong learner.
Interesting. Learning from mistakes, step by step.
Right. And because each model is refining the previous one, boosted trees often achieve even higher accuracy than random forests.
But there's a catch.
There can be. They can be more prone to overfitting if you're not careful with tuning them. And because they're sequential, you have to train one before you can train the next. They're generally slower to train than random forests.
Gotcha. Any famous boosting algorithms?
Oh, yeah. AdaBoost was an early one. Gradient boosting is very common. And XGBoost is incredibly popular now, known for its performance and optimizations.
Great contrast. Parallel versus sequential learning in ensembles.
Okay.
Now, for the one you mentioned at the start, the current king of the hill, really reshaping AI neural networks.
Right. Let's circle back to that idea of implicit feature engineering. Remember trying to recognize handwritten digits?
Yeah, how a simple model struggles because a 1 can look slightly different each time.
Exactly. A human looks at a 1 and sees features like a main vertical line, no loops. But a computer just sees pixel values initially.
It doesn't know vertical line means anything.
Not inherently.
Yeah.
Now, we could try to manually create features like count the vertical lines or find enclosed loops, but that's hard and might miss important patterns.
So the network has to learn those features itself. Like the SVM kernel trick, but maybe even more automatic.
Precisely. Artificial neural networks are designed to implicitly and automatically figure out these complex features for us.
How do they do that?
By adding extra layers of computations, what we call hidden layers, filled with unknown variables or neurons between the raw input, pixels, and the final output, the digit classification.
Hidden layers. So connecting this to the bigger picture, that's where the deep learning comes from.
That's exactly it. Instead of the input pixels directly predicting the output digit, the inputs predict the values in the first hidden layer. Those hidden layer values then predict the values in the next hidden layer, and so on.
Until the final layer predicts the actual digit.
Right. And in that process, those hidden layers learn to represent increasingly complex features. A first hidden layer might learn to detect simple edges or corners from the pixels.
Okay.
A later layer might combine those edges to detect shapes like loops or longer lines.
So it builds up complexity, layer by layer, like how our own brain processes visual information.
That was the original inspiration, loosely. The key is that we don't tell it what features to find. It discovers features like horizontal line here or curve there, simply because those features help it make better predictions.
Even if we don't know exactly what a specific neuron in a hidden layer represents?
Often we don't. We might not have a clear, human understandable label for a feature learned by a deep layer, but if it helps the network distinguish a 3 from an 8, the network keeps it and uses it.
And deep learning just means using many of these hidden layers.
Yes. Stacking many layers allows the network to learn incredibly complex hierarchical features. Think about recognizing a face in a photo that requires detecting edges. Then simple shapes, they're parts of faces like eyes and noses, then the whole face configuration. Deep networks excel at this automatic feature hierarchy learning.
Mind-blowing stuff. The machine building its own representation of the world from raw data. Okay, that's been a fantastic tour of supervised learning. But we started by mentioning two branches.
Right. We can't forget unsupervised learning.
The one where we don't have the answers beforehand.
Exactly. Everything we just discussed, regression, classification, neural nets for those tasks, that's all supervised. You need labeled data. But sometimes you don't have a specific target to predict. You just want to find structure, patterns, relationships hidden in the data.
Things you didn't even know to look for.
That's the essence of unsupervised learning.
And a really common unsupervised task is clustering, right? Finding groups. It sounds a bit like classification, but you emphasized earlier it's different.
Very different conceptually, yes. Remember, classification is supervised. You predict known categories, cat, dog, using labeled examples. Clustering is unsupervised. You have no labels, and you want the algorithm to find unknown groups, the clusters, just based on similarity in the data itself.
Finding natural groupings.
Exactly. You might look at data plotted in 2D and easily spot, say, 3 distinct clumps. But imagine having data with hundreds of dimensions. Humans can't visualize that. Algorithms are needed to find those clusters.
Okay, and the most famous clustering algorithm is?
K-means clustering, very widely used.
Another K, like K nearest neighbors. What does the K mean here?
Same idea, it's a hyperparameter you have to choose. Here, K is the number of clusters you were looking for.
Oh, so you have to tell it up front. I think there are probably 3 groups in this data.
Typically, yes. And just like with K and N, finding the right K is often an art. It involves trial and error, maybe some domain knowledge about your data. Is it customer segmentation? Maybe you try K3, K5, K10, see what makes sense.
Okay, so you pick K. How does K-means actually find the clusters?
It's an iterative process, actually quite intuitive.
Walk me through it.
Okay. Step 1. Randomly place K points in your data space. These are your initial cluster centers or centroids.
Just random guesses to start.
Yep. Step 2. Assign every single data point to whichever cluster center it's closest to.
So every point now belongs to one of the K clusters.
Right. Step 3. Recalculate the position of each cluster center. You do this by finding the mean, the average position, of all the points currently assigned to that cluster. The center moves to the middle of its assigned points.
Okay, the centers shift.
Then you repeat Step 2 and Step 3. Reassign points to their new nearest center. Recalculate the centers based on the new assignment.
You keep doing that. When does it stop?
You keep iterating assign, recalculate, until the cluster centers stop moving much, or the points stop changing which cluster they belong to. The clusters have stabilized.
It sort of settles into a final grouping. Makes sense. Are there other clustering methods?
Oh, absolutely. K-means is popular because it's simple and fast. But other algorithms exist that don't require you to pre-specify K, or that can find clusters that aren't just simple spherical shapes. But K-means is the classic starting point.
Good to know. Okay, one more major area in unsupervised learning. Dimensionality reduction. Sounds like simplifying data, tidying up.
That's a perfect way to think about it. Decluttering your data. The core idea is to reduce the number of features, the dimensions in your data set.
Fewer columns in your spreadsheet, basically.
Right. But you want to do this while keeping as much important information as possible.
Losing the noise, keeping the signal.
Exactly. These algorithms typically work by finding correlations or relationships between your existing features, and then combining or removing redundant dimensions without losing the core structure of the data.
Like recognizing an airplane in a photo, even if you make the image much lower resolution, you lose pixels, dimensions, but keep the airplane-ness.
Great analogy. You retain the essence.
And why would you want to do this? What's the benefit?
2 main benefits, really. One is just understanding your data better, finding the underlying relationships between features.
You seem what's truly important.
Yeah. And the second is as a pre-processing step before you do supervised learning. Reducing dimensions can make your classification or regression algorithms run faster, use less memory, and sometimes even perform better because you've removed noise. Makes them more robust.
Okay, that makes sense. So how does it work? What's a key algorithm here?
The most common one is principal component analysis, or PCA.
PCA.
Okay,
Yeah.
Let's think of an example. Imagine you're trying to predict different types of fish based on features like their length, their height, maybe their color, number of teeth, lots of measurements.
Lots of dimensions.
Now, this raises an important question. What if features like fish length and fish height are really highly correlated? Taller fish tend to be longer fish.
Well, they probably go together.
So, including both height and length might not actually add much unique information. It could even just add noise, making it harder for your prediction model.
So instead of two correlated features, could you maybe combine them into one feature that captures, like, the overall shape or size aspect?
Exactly what PCA tries to do. It finds the directions in your multidimensional data where the data varies the most. These directions are called the principal components.
The directions of greatest variance.
Yes. In the fish example, the direction of most variance might be a diagonal line that combines length and height, capturing that shape idea you mentioned.
Yeah.
That becomes your first principal component, your most important new feature.
And then it finds the next most important direction and so on.
Right. It finds these components in order of how much variance they explain. And often, you find that just the first few principal components capture almost all the important information.
So you can just keep those first few components and discard the rest.
Exactly. You might start with 50 features, run PCA, and find that maybe the first 5 or 10 principal components capture 95% of the variance in the original data. So you just use those 5 or 10 new combined features instead of the original 50.
Dramatically reducing the dimensions while keeping most of the essence. Very clever.
It's incredibly useful, especially for really high-dimensional data sets. Simplifies things massively, often with little loss in final performance.
Wow. Okay. We have covered an incredible amount of ground today, seriously.
We really have, from the basic split.
Supervised versus unsupervised.
Yeah, then into supervised. Regression, classification, specific algorithms like linear and logistic regression, KNN, SVMs.
Decision trees, the ensemble methods like random forests and boosting.
And of course the big one, neural networks and deep learning.
Right. And then we jumped into unsupervised, clustering with k-means and dimensionality reduction with PCA.
It's a lot, but hopefully listeners now have that intuitive feel we aimed for.
I think so. You should now have a much better grasp of these major algorithms, how they differ, what kinds of problems they're good for. It's like having a mental toolkit.
Our hope is definitely that this deep dive empowers you, lets you look at data problems, or even just AI news with a new understanding.
So thinking about that, what does this all mean for you listening right now that you have this foundation? What kind of unseen data out there could you maybe start exploring, knowing how these algorithms find patterns?
Yeah, and how might your understanding of the technology you use every day, from your spam filter to photo apps, recognizing faces, how might that change? Just knowing these fundamental basics we talked about.
Something to think about.